Welcome. A couple of lectures ago, we asked the question, what are the stars? And we discussed the question. Today we are going to ask the second half of the question, namely, why are the stars as they are? More specifically, I shall be discussing Eddington's theory of the stars. Let's recall what we have discussed so far. Lane, Kelvin, Helmholtz, Emden, and others in the 1870s advanced the hypothesis that stars are globes of perfect gas that obeys Boyle's law. In other words, the inward-directed gravitational pressure is balanced by the outward-directed gas pressure, and they said that this gas pressure should be calculated according to Boyle's law. The principle of hydrostatic equilibrium we set up was that if you consider an elemental cylinder of length dr and cross-sectional area unity, then the gravitational force acting on it due to the mass interior to that cylinder must be balanced by the pressure differential across the two surfaces of the elemental cylinder. In other words, dP with the difference in pressure must be equal to minus gm rho dr over r squared, where m of r is the mass interior to r and rho is the density at the radial distance r. Now we argued that this works in the following way. Consider that elemental cylinder, which I have now depicted as a slab of material, is the same thing. It's being bombarded from below and above by particles whose average kinetic energy is 3/2 kT. As we go down, the density as well as the temperature increases. Therefore, the energy of these particles is more than the energy of these particles. There are also more particles per unit volume below than above, and therefore there is a net pressure differential between the two surfaces. What is Boyle's law? Boyle's law states that the pressure of a gas, an ideal gas, is nkt, where n is the number of particles per unit volume. Well, in the context of gravity, it is more advantageous for us to cast this formula in terms of the mass density rho rather than the number density m. The two are obviously related by mass density divided by the mass of the particle is equal to the number density. Now, in the case of Boyle's law, all particles contribute equally to the pressure because they all have the same amount of energy, 3/2 kT. And therefore, one has to introduce the notion of a mean molecular weight to account properly for the total number of particles. Therefore, the number of particles per unit volume in the formula above has been replaced by the mass density rho divided by mu mp, where mp is the mass of the proton and mu is the mean molecular weight. So here is the equation of hydrostatic equilibrium. It says that dP by dr is minus gm rho over r squared, and the pressure has to be calculated according to Boyle's law. This was the earlier theory. Now in 1923, Sir Arthur Eddington in Cambridge University made an important addition to this theory. He stated that stars are globes of gas in which the inward pull of gravity is balanced by the combined effect of the pressure of an ideal gas and the pressure of radiation. The essential new physics that Eddington introduced was radiation pressure. We will see that in more massive stars, which become neutron stars, black holes, and so on, radiation pressure is far more important than gas pressure. And radiation pressure is to be calculated according to the law 1/3 AT to the power 4, where A is Stefan's constant. Now, just as we did for particles bombarding the unit cylinder from below and above, let us now consider radiation flux incident from both from the left and to the right. the temperature is larger on the left side than on the right-hand side. Therefore, the radiation flux moving from left to right, which is F plus, will be more than the radiation flux F minus going from right to left. So, Eddington's theory says that you must balance the gravitational pressure by a combined effect of gas pressure and radiation pressure. Therefore, the equation of hydrostatic equilibrium, remains the same, E, the total pressure on the left-hand side, is now a sum of gas pressure plus radiation pressure. Gas pressure is to be calculated once again according to Boyle's law, and radiation pressure is to be calculated according to Stefan's law. So this is the important addition that Eddington made. And as you will see, it has some very dramatic consequences for the stars. Now, let us consider what this flux of radiation does to the slab. So here I am considering radiation from the left, whose flux is F. Flux is energy per unit area per unit time. And that is incident on a unit area whose thickness is dx and x is this direction. Now, the fraction of this radiant flux which is absorbed by this slab will be the incident flux F multiplied by kappa rho dx, where kappa is the mass absorption coefficient per gram. You remember in the third lecture, when we discussed the principles of radiative transfer, we introduced the concept of absorption coefficient per length ds. Very often it is more advantageous for us to define the mass absorption coefficient per gram of material. The two are obviously related. Now, what is the mass of this elementary cylinder? It is the volume of the cylinder. Volume of the cylinder is the area 1 multiplied by dx. Therefore, dx is the volume. So, rho times dx is the mass of the slab. And kappa rho dx times F is the fraction of the flux absorbed by the slab. Now, this flux that is absorbed can be written in terms of momentum that is absorbed by dividing by the speed of light. Why do I divide by the speed of light? You will remember, for a photon, the momentum of a photon is energy divided by c, or h nu divided by c. Therefore, for a fully relativistic gas of particles, the relation between momentum and energy is momentum is energy divided by c. So, this is the x component of the momentum absorbed by this slab. That's the same thing over there. The reason why I have written it once again is in the discussion just now, I have assumed that the flux is normal to the slab. Now, there is no guarantee that the flux is going to be normal to the slab. The flux may be incident at an angle theta, such as shown there. Convince yourself that the result, that the x component of the flux absorbed or the momentum absorbed will be F kappa rho dx by c, remains unchanged even if the flux is incident at an angle theta. It should take you more than a few seconds to convince yourself of this. Very good. Now, let us consider the real situation where there is flux incident both from below and from above, shown in this picture as coming from left to right. So imagine this figure being rotated by 90 degrees. Therefore, there is a net outward flux, which is F plus minus F minus. So the net outward flux going in the positive x direction or the positive r direction, which is towards the surface of the star, is the difference between F plus minus F minus. Now, the net positive momentum gained by the slab will be, as we discussed before, F times kappa rho dx divided by c, where F is now the net outward flux. Now, here is the important point. Please pay attention to this. For the slab to be in radiative equilibrium, in other words, it's not for the slab not to be blown away by the pressure of the radiation, the momentum gain, which is indicated over here, must be absorbed fully by the slab. It must be absorbed and converted to a pressure differential, which is now given by dPr, PR for radiation pressure, F kappa rho dx by C, and I put a minus sign to indicate that the pressure is decreasing as we go outwards, and since x direction, positive x direction is defined as going outwards, I have to put a minus sign to get the convention right. So please convince yourself that I have not done anything wrong or committed a fraud by putting a minus sign. So let me say once again, there is a net energy flux which corresponds to a net momentum flux. A fraction of that is absorbed. For the slab to stay in hydrostatic equilibrium, that momentum flux that is absorbed must be converted to a pressure differential across the two surfaces. Now this pressure differential due to radiation now will be an additional pressure differential which will help to support the star against gravity. What do I mean by that? Let's go back to our equation of hydrostatic equilibrium. We said dP is the pressure differential between the bottom and the top surfaces of this elementary cylinder, and that is our equation of radiative transfer. And we said that the pressure is a sum of gas pressure plus radiation pressure, and therefore dP is a sum of dP gas plus dP radiation. So both gas pressure and radiation pressure contribute to supporting that elementary cylinder against the inward directed gravitational pull. And what is dP radiation? That is the formula we had derived earlier, which is the net outward flux multiplied by kappa rho dr divided by C. I'm sorry I changed the notation from X to R to be consistent with this figure. Now, we have been considering an imaginary surface of radius small r, whose surface area is 4 pi r squared. And over there we were considering an elementary cylinder of length dr. And we said the flux, net flux incident on it is capital F. Now let us write that net flux, outward flux, capital F, in terms of the luminosity emanating from the center. Since the luminosity is going in all directions, clearly the luminosity divided by 4 pi r squared is the energy per unit time incident on a unit surface area of this sphere, which is of course the flux. Flux is energy per unit area per unit time, whereas luminosity is energy per unit time. There is no surface area that comes in there. So I can now use that expression and say, let us now consider a star where there is no gas pressure at all. A star which is in pure radiative equilibrium. That means that this elementary cylinder is supported against the inward pull of gravity, which is gm rho by r squared, solely by the pressure differential between the two surfaces due to radiation. And that we calculated as kappa F kappa rho dr divided by C. Now let us replace flux F by the luminosity using the relation F is equal to L by 4 pi r squared. Then, if I now put this expression into this and this expression into that, convince yourself that I can solve for the luminosity, and that expression for the luminosity reads 4 pi c Newton's constant of gravity, mass of the star multiplied by the mass of the hydrogen atom divided by Thomson scattering cross-section. Now you'll say this is a complete fraud, because in this expression there is no mass of hydrogen atom and there is no Thomson scattering cross-section. What is there is the opacity kappa. Well, don't be worried. It's the same thing. I haven't committed any fraud. The mass absorption coefficient is related to the scattering cross-section by the relation kappa rho is equal to n sigma, where n is the number of scatterers per unit volume and sigma is the scattering cross-section of each absorber or scatterer. Therefore, I can write the opacity kappa in terms of the scattering cross-section, and since the scattering is mainly due to electrons, why is it mainly due to electrons? We use virial theorem to convince ourselves the internal temperatures of stars are more than 10 million Kelvin or so, and therefore all atoms will be fully ionized, and therefore we'll be dealing only with nuclei and electrons. And Thomson scattering of nuclei is unimportant because their masses are 2,000 times more than the masses of the electron. Therefore, it's only electron scattering that matters. And therefore, I have replaced opacity kappa by the mass of the hydrogen atom divided by the Thomson scattering cross-section. Please convince yourself of this elementary algebra. Why have I written it in this form, and what is the significance of this result? Let me repeat once again. What we are considering is a star which is in pure and exclusive radiative equilibrium. There is no gas pressure. So what balances the inward pull of gravity is the radiation pressure gradient. And we said that the luminosity of such a star in radiative equilibrium will be equal to this. Therefore, if the luminosity of the star were to exceed this value, then radiation pressure will overwhelm gravity and the star will be blown apart. So this value of luminosity is the maximum luminosity a star can have. Using the principle of radiative equilibrium, just as we just now did, Eddington derived the maximum possible luminosity a star can have. What is the physical significance of this? It is that if the luminosity were to exceed this value, radiation pressure will blow apart the star. This limiting luminosity is known in the literature as the Eddington luminosity limit. And this concept plays an extremely important role in contemporary astronomy and astrophysics, in particular high-energy astrophysics, and its importance is not confined to stars, as we shall see in later lectures. So let me rewrite the formula that I had written before and give it the name L. Eddington in honor of Sir Arthur Eddington. The maximum luminosity a star can have is given by 4 pi c g mass of the star, mass of the hydrogen atom, divided by sigma Thomson. Remember, sigma Thomson is 8 pi by 3 into E squared over mc squared whole square. And the numerical value of the left-hand side per solar mass is 10 to the power 38 ergs per second. In other words, a star with a mass equal to m solar, then this ratio becomes 1, cannot radiate more than 10 to the power 38 erg per second. If it did, it will blow apart the star. So if a star is 1,000 times more massive than the sun, then the Eddington luminosity is 1,000 times 10 to the power 38 ergs per second. To me, this is one of the most beautiful results in all of physics, because it's saying that apart from fundamental constants, the maximum luminosity a star can have is uniquely and solely determined by the mass of the star and the mass of the star alone. Isn't that a beautiful result? So let me say once again, apart from fundamental constants that you see over there, the maximum luminosity of a star is determined solely by the mass of the star. Very good. And we shall return to this concept when we discuss quasars and why the central engine have to be supermassive black holes and so on. Now let's get back to a story of a star in radiative equilibrium where gas pressure is also present. We said the net outward flux is given by the flux going from below to outwards and minus the flux going inwards. Net positive momentum, we said, is F times kappa rho dx or dr divided by the speed of light. For a slab to be in radiative equilibrium, this momentum gained per second by the slab must be fully absorbed and converted to a pressure gradient. And that pressure gradient is given by F kappa rho dr divided by C. So that formula can be rewritten by solving for the net outward flux F. Therefore, the net outward flux from the star is minus C over kappa rho multiplied by dPr by dr, where PR is the pressure of radiation, and the pressure of radiation is to be calculated according to Stefan's law, 1/3 A to the power 4. Therefore, the net outward flux is equal to minus AC divided by 3 kappa rho d by dr of T to the power 4. An extremely important and beautiful result, a magical result. Now, let us once again rewrite this formula in terms of the luminosity by remembering that the luminosity divided by the surface area of the sphere, which is 4 pi r squared, will be the net outward flux. Flux is by definition energy crossing a unit area per unit time. Therefore, the luminosity crossing is the same formula. I'm dividing by 4 pi r squared, taken 4 pi r squared to the right hand side, and I have written a formula now for the luminosity L of r crossing an imaginary surface whose radius is small r, which is given by minus AC divided by 3 kappa rho d by dr of T to the power 4 multiplied by the surface area of that imaginary sphere. A is Stefan's constant, kappa is the opacity of the star, mass absorption coefficient per gram of material. Now, I read it in the formula once again to underline the following important thing. Please notice that the luminosity is determined by the temperature gradient and by the opacity. It says that if we know the temperature gradient of a star and if we know the opacity, we can predict the luminosity of the star. This is magical. Now you would say this is complete nonsense because stars of different masses will have different luminosities. Stars of different masses will have different radii and therefore different temperatures. You told us that the energy stars radiate is generated at the center by fusion reaction, and that surely depends upon temperature. So how can the luminosity crossing an imaginary surface depend only on the temperature gradient and the opacity? Even the opacity doesn't really matter because it's mostly hydrogen, it is ionized, therefore opacity is due to Thomson scattering cross-section, so we know that also. Therefore we are saying that the luminosity of a star is more or less uniquely determined by the temperature gradient. This is a magical result. If the star were to generate a little more luminosity, I create some mischief, then the star will change the temperature gradient because the star has to be in radiative equilibrium, and therefore the luminosity will decrease and you'll come back to this original value. So there is a feedback there. So I would like you to think about this, only then you will appreciate that this is a truly magical result. So what we have done now is to introduce the concept of radiative equilibrium, And the equation of radiative equilibrium is L of R is equal to minus AC by 3 kappa rho d by dr of t to the power 4 multiplied by 4 pi r squared. What does this radiative equilibrium mean? It means that the net outward flux of radiation is converted to a pressure gradient, which adds to the pressure gradient of the gas pressure, and the two together balance gravity. So that's what radiative equilibrium means. Now there is another equation, which is the mass equation, and it's a very simple equation. Let us imagine a spherical shell of radius r, surface area 4 pi r squared, of thickness dr. And let us ask, what is the mass contained in that shell? The mass contained in that shell is simply the volume of the shell, which is 4 pi r squared times the thickness of the shell, multiplied by the density. Now I can divide by dr and write the mass equation as dmr by dr is equal to 4 pi r squared times the density at the radius r. The final equation is the equation of thermal equilibrium. Energy is being radiated away by the star, luminosity, according to the formula that we wrote down. But this energy which is being radiated away must be compensated by energy that is being generated near the center of the star. Now let epsilon be the energy generated per gram of material per second. So epsilon is energy generated per gram per second. Now, what will epsilon depend upon? Clearly, epsilon will depend upon the temperature, the density, and the chemical composition, whether it's hydrogen or helium or carbon or oxygen. The total luminosity L of R crossing an imaginary surface of radius R is given by, I'm considering an imaginary surface of radius small r. Let's start at the center of that sphere and construct a shell whose radius is r, whose surface area is 4 pi r squared, whose volume is 4 pi r squared dr, its mass is rho into 4 pi r squared dr. Therefore, the total energy that is generated per unit time there is epsilon into this mass. You integrate that from 0 to the imaginary surface of radius r, and that is the luminosity crossing the surface of radius r. Now, that equation can be written as a differential equation. dLr by dr is equal to epsilon rho multiplied by 4 pi r squared. So all I'm saying is the energy that is radiated to an imaginary surface of radius r must be compensated by the energy that is generated inside that imaginary surface. So let us write down, let us gather together the various equations of stellar structure in Eddington's theory. First and foremost is the equation of hydrostatic equilibrium, where the pressure is the sum of gas pressure plus radiation pressure. Second is the equation for radiative equilibrium. And third is the equation for thermal equilibrium. Luminosity is compensated by the energy generated per unit time, and the mass equation. So there are 4 equations. Therefore, to solve for a model of the star, you have to integrate these 4 equations, solve them in a self-consistent manner. So that's not a trivial job, but it can be done. And Eddington did that in his famous book written in 1923. Today, of course, with very fast computers, you can do a marvelous job. What are the inputs that are needed to construct a model of the star based on these 4 equations? The inputs are, first and foremost, the equation of state, namely an equation that gives you pressure as a function of density and temperature. It may be Boyle's law, it may be something else. Secondly, you must give the chemical composition, whether it's hydrogen or helium or carbon or their mixture, then how much of each element is present. Then you must specify the opacity, and then you must specify the rate of energy production. If you have these inputs, then you can solve these four equations self-consistently, then you have modeled the star. Now let's go back to Eddington's theory and pull out of it a magical relation, which is the relation between the mass of the star and the luminosity of the star. There is the equation for radiative equilibrium. Now, let us write this a scaling relation. What I mean by scaling relation is the following. This is obviously a differential equation, and we should treat it with respect, but we can also ask, how does it scale with the radius? How does it scale with the temperature? How does it scale with the mass? That's known as scaling relation. So scaling relation is luminosity is proportional to RT to the power 4 divided by m. Where does it come from? So there is T to the power 4, there is R squared, there is an R. I can write dt to the power 4 by dr as T to the power 4 divided by capital R. This is a capital R. The density rho is mass divided by R cube. So R cube goes in the numerator. R cube into R squared is R to the power 5 divided by R will give me R to the power 4. Therefore, we have this beautiful scaling relation that the luminosity of a star in radiative equilibrium is of the order of RT to the power 4 divided by m. Now, let us pull out the magic from this. You know the equation of hydrostatic equilibrium says dPdr is Gm rho over R squared, where P is the sum of gas pressure plus radiation pressure. But for the sake of simplicity, let us leave radiation pressure and consider only gas pressure. For a star like the Sun, radiation pressure is only 10% or even less than 10%. Therefore, Boyle's law pressure is rho T, rho kT. K is not important here because I'm writing down scaling relation. So the left-hand side is rho T divided by R, and the right-hand side is m rho by R squared. Rho cancels out, 1R cancels out, and I get the relation by taking the R over there. I get the relation RT is proportional to m. Now, I can now put that relation into that, and I get a magical relation that the luminosity of a star is proportional only to the mass and the cube of the mass. This is not surprising because one would have thought that the luminosity of a star of a given mass depends on what radius and therefore what temperature it has. But we are saying it doesn't matter, it's only the mass that matters. That is because in radiative equilibrium, R and T comes as a combination RT, and RT is proportional to the mass. Therefore, this magical relation that luminosity is determined by the cube of the mass, I don't care about the temperature or the radius, is true, and it derives from the fundamental principle of radiative equilibrium. Let us compare this with observations. Eddington compared it with observation. What is shown on the y-axis is the luminosity of the star increasing, going from bottom to the top, and what is on the x-axis is the mass of the star. The dots are observational data available to Eddington in 1923, and the solid curve is L proportional to m cube. Now you will agree that this is an extremely good description of the actual mass-luminosity relation of observed stars. Now today, in 2022, if you look at the latest data, which cover stars of vastly greater luminosity range and mass also, then you find that the luminosity isn't quite proportional to m to the power 3, but m to the power 3.5. But that's fine. Eddington was dealing with this region over there at that time. So I think this is a very remarkable thing. Therefore, we can continue to say, even though the exponent is 3.5 observationally and not 3, we can continue to say that the luminosity of a star depends only on the mass. Therefore, larger the mass, larger the luminosity. Now, let us ask the question, why are the stars as they are? What do we mean by that question? Now, to Eddington, this agreement between the mass-luminosity relation he had derived and the experimental points was most annoying. Eddington said in his book, "What business have they on a curve reserved for a perfect gas?" What did he mean by that? The stars he had calculated were stars in which the gas pressure is calculated from perfect gas law, namely Boyle's law. But the data pertains to real stars. Whoever said that the real stars, gas obeys Boyle's law? Why shouldn't they? Well, he said, what should we make of this agreement between the prediction made for stars made of perfect gas and the data pertaining to real stars? Is it possible, he asks, is it possible that the stellar material of even the dense stars are perfect gas? But this would require that gas of density in excess of density of iron would behave as a perfect gas. Now, if you said that, people will laugh you out of the room, because by the time gas condenses to a density of 1 gram per cubic centimeter, that gas is now a liquid and it is no more an ideal gas. The fact that it is a liquid, the fact that it has undergone a phase transition from gas to a liquid is because of interaction between the molecules. Therefore, it is anything but an ideal gas. But then if you have a star whose density is greater than the density of iron, surely it's ridiculous to think that those stars, in those stars, gases obey Boyle's law. Therefore, how come real stars seem to sit on the curve that Eddington had drawn for ideal gas? To quote Eddington, the reason why it should not is earthly, and does not apply to the stars. So he says, in stars, in real stars, even though the central density may be well in excess of the density of iron, the gas obeys Boyle's law. And the reason why it doesn't on Earth is earthly, and earthly arguments do not apply to the star. Beautiful argument, and this is the way he writes the book also. So he says, our mistake was that in estimating the congestion in the stellar ballroom, we had forgotten that crinolines are no longer in fashion. Crinolines are these gigantic skirts with a bamboo support that women wore in Victorian days. So you see, here is a waiter trying to serve something during a party, and he has this long spoon in order to be able to reach the beautiful lady. So Eddington says, our mistake was in estimating that ladies still wear crinolines. What does crinolines and ladies wearing crinolines have to do with perfect gas? But that's what Eddington said in his book, and this is what he meant. So these are atoms in a gas. The central dark dot is the nucleus, whose dimensions are of the order of 10 to the power minus 13 centimeters, and the atoms themselves are of the size 10 to the power minus 8 centimeters, and the distance between the atoms are very large compared to the sizes of atoms. Therefore, the interaction energy between the atoms is small compared to their kinetic energy, and therefore a gas can be regarded as an ideal gas. But by the time When you compress the gas and it becomes a liquid, you notice that the atoms have come very close to one another. Therefore, the electronic shells of the adjacent atoms begin to interact with each other due to van der Waals forces, and therefore a liquid is anything but ideal. Potential energy of interaction between molecules is far more important than their kinetic energy. But we are not dealing with an ordinary gas or an ordinary liquid in a star. We are dealing with a material which is at a temperature of 10 million degrees or more. 10 million degrees or more, the atoms are completely ionized. And therefore, the distance between the individual particles, whose sizes are of the order of 10 to the power minus 30 in centimeters, is now 10 to the power minus 8 centimeters. Therefore, the individual particles in a plasma are very far apart. And therefore, their interaction energy can be neglected in comparison with their kinetic energy. Please remember that the density of this plasma, mass per unit volume, is the same. But what we are saying is the distance between the particles is very large because the atoms are ionized. You are walking in an extremely crowded street on a rainy day, everybody has an umbrella, and these umbrellas are rubbing against each other. Suddenly the rain stops, everybody closes their umbrella, people don't rub against each other. So that is the reason why a theory built for ideal gas stars brilliantly explains the data of real stars. So that is the first part of the question, why are the stars as they are? The second puzzle that Eddington pointed out is why are the masses of the stars in an incredibly narrow range? The masses of the stars are in the range between half times the mass of the sun to about 50 times the mass of the sun. Why aren't there stars 1,000 times the mass of the sun or 1,000,000 times the mass of the sun? Why aren't there stars of the size of planets? Why aren't there stars of the size of football? Now, Eddington tried to answer this question with a story, a parable of a physicist on a cloud-bound planet. There's a very clever physicist living on a planet which is permanently clouded. So he has never seen the sky. He has never seen the star. But he's a very clever physicist and he knows the laws of physics that have been determined in the laboratory. So he constructs objects in which the inward pull of gravity is balanced by the outward pressure due to gas and radiation. And he calculates a table where the first column is the mass of the globe, 10 to the power 30 grams, 10 to the power 31 grams, 10 to the power 32 grams, and so on. The second column is radiation pressure. The third column is gas pressure. So you find there is 0.0000, 0.999, here is 0.000, 0.999. What he finds that only in an incredibly narrow range of masses, between 10 to the power 33 grams and 10 to the power 35 grams, these two columns are of comparable value. You're not dealing one column full of zeros, other column full of nines. They become comparable. So the physicist in the cloud-bound planet says the rest of the table would consist mainly of long strings of nines and zeros. Just for the particular range of mass, about the 33rd and the 35th globes, the table becomes interesting and then lapses back to nines and zeros. Regarded as a tussle between matter and ether, regarded as a tussle between gas pressure and radiation pressure, the contest is overwhelmingly one-sided, except between numbers 33 and 35. And we may expect something interesting to happen. What happens is the stars. We draw aside the veil of cloud beneath which our physicists have been working and let him look up at the sky. There you will find 1,000 million globes of gas, nearly all of mass between his 33rd and 35th globe. That is to say, between half and 50 times the sun's mass. The lightest known star is about 3 times 10 to the power 32 grams, and the heaviest about 2 times 10 to the power 35 grams. The majority are between 10 to the power 33 and 10 to the power 34 grams, where the serious challenge of radiation pressure to compete with gas pressure is beginning. So Eddington says the happening of stars has to do with this tussle between gas pressure and radiation pressure. So that is what he said in his book. But Eddington was obscure about two things. Why do the stars have nearly the same mass? He didn't explain why the tussle between gas pressure and radiation pressure have to do with stars coming in an incredibly narrow mass range. Second, this is what I already said. Why is an interesting tussle between gas pressure and radiation pressure important for the happening of stars? Now, this was answered by Subramaniam Chandrasekhar in 1937. He was a young man of 26 years old at the time. He sent a postcard to the great physicist Paul Dirac in Cambridge, in which he had solved this problem. And Paul Dirac thought that this was a sensational argument and sent it to the prestigious journal Nature and got it published. This is what Chandrasekhar said. Let us ask after Chandrasekhar the following question first. Why are the atoms as they are? Why don't we have atoms of the size of the nuclei? Why don't we have atoms which are as big as a ball bearing? Why don't we have atoms as big as a football? And he says the answer is the following. Atoms are as they are because they obey the rules of atomic physics. What are the rules of atomic physics? The centrifugal force experienced by the electron is balanced by the attractive Coulomb force. And angular momentum comes in multiples of Planck's constant. These are the two rules of quantum physics, and these are the rules that atoms have to obey. And the atomic theory, which was constructed by Niels Bohr, provides a length scale with which to measure them, namely the Bohr radius. In other words, this very simple theory of the atom, namely centrifugal force is balanced by Coulomb attraction and angular momentum is quantized, that theory has fundamental constants, Planck's constant, mass of the electron, charge of the electron, and so on. And it gives you this combination, h squared divided by 4 pi squared me squared, which is a dimension of length. It says objects which obey these rules of atomic physics must be of that size. What is that size? Half an angstrom, 0.5 into 10 to the power minus 8 centimeters. This is why, if you go over the entire periodic table, the sizes of atoms are of the order of the Bohr radii. They may be 10 times the Bohr radius, they may be 50 times the Bohr radius, but you don't have an atom which is a million times the Bohr radius or a billion times the Bohr radius. You don't have atoms as big as a ball bearing or as big as a cricket ball. So atoms as they are, because atoms obey atomic physics, and atomic physics gives you a length scale with which to measure the sizes of atoms. In a similar manner, one can ask, why are the stars as they are? Why are the masses of the stars as they are? Now, what Chandrasekhar showed was that the theory of stellar structure has fundamental constants appearing in it. And a certain combination of fundamental constants is the dimension of a mass. And he says those objects which have to be explained using the equations of stellar structure will have masses of the same scale as the characteristic mass which emerges from the combination of fundamental constants. And the combination of fundamental constants he isolated was hc divided by g to the power 3 halves, which is the dimension of cube of a mass, divided by the square of the proton mass. So the right-hand side is a dimension of a mass. So this, like Bohr radius, is the combination of fundamental constants that appear in Eddington's theory, which is the dimension of mass. Therefore, objects that obey Eddington's theory should have this kind of mass. And what is the numerical value of this mass? 29 times the mass of the sun. Therefore, Chandrasekhar said, just as Bohr radius is the characteristic size of objects obeying the rules of quantum theory of atoms, the characteristic mass of objects in which gravity is balanced by the combined pressure of the gas and radiation must be approximately 10 to the power 34 grams. Beautiful argument. So now we know why the phenomena of star, why the happening of stars occurs only in an incredibly narrow range of masses. What are the implications of Eddington's theory for the lifetime of stars? He said that the luminosity of a star is proportional to m to the power 3 in Eddington's theory, but observation tells us it's m to the power 3.5. The total energy a star can manage to raise is of the order of mc squared. Therefore, the lifetime of the star is the total energy the star can have, which is mc squared, divided by the rate at which it is radiating energy, which is the luminosity of the star, which is proportional to m to the power 3.5. Therefore, the lifetime of the star is proportional to 1 over m to the power 2.5, a rather steep power of the mass. So according to this formula, the sun will shine for 10 billion years. We know the sun is already 5 billion years old. It will shine merrily for another 5 billion years or more. But a star, which is 10 times the mass of the sun, the kind of star that will collapse to a neutron star or black hole, will live only for 10 million years. Now this is an incredibly short time scale in astronomy. So these are some of the extraordinary conclusions Eddington drew from an incredibly simple theory of the stars. I would strongly urge that you read Eddington's book, which was published in 1923, The Internal Constitution of the Stars. This is now available at throwaway prices. Go to Amazon and you'll be able to get this price for a book for about 100 rupees or 200 rupees. It is worth reading because it is a classic. So with that, we conclude this lecture on why are the stars as they are. And in the next lecture, we shall discuss another interesting question, namely, how do the stars generate the energy they radiate? Again, that will be a story of Eddington. Thank you very much.